In this video, we will be looking at the cross product, and we will be starting with the cross product of geometric vectors. As a reminder, a geometric vector is defined by its magnitude and direction. Now, before we get into that, there are some physics concepts like angular momentum, magnetic force, torque, that require that we multiply the magnitude of one vector by the magnitude of the component of the other vector that is perpendicular to the first. This is the magnitude of the cross product. So based on what we just read there, let's try to come up with the cross product magnitude definition. So on the following diagram, I have two vectors, u and v, and the angle between them, which is theta. We're told we need to multiply the magnitude of one vector. So I'm going to say the magnitude of vector u by the magnitude of the component of the other vector that is perpendicular to the first. Okay, so I need a vector that is perpendicular to u, but is the component on the other one. So let me draw that in. I'm just going to call this the component. Now this component is perpendicular to vector u, and we need to figure out the magnitude of this component for vector v. Well, we can do that with a little bit of SOHCAHTOA. So the component is the opposite, and the magnitude of vector v is the hypotenuse. So just on the side here, I'll write sine theta equals the component over the magnitude of v. And what do we end up getting? For that perpendicular component, we get the magnitude of v times sine theta. So let's go back to that definition. Multiply the magnitude of one vector, so vector u, by the magnitude of the component of the other vector that is perpendicular to the first. And we just found that that is vector v times sine theta. And this is equal to the magnitude of the cross product between u and v. So let's see how that plays out with a physics application, specifically torque. Now, torque is the turning effect, and it is a measure of the force acting on an object that causes it to rotate. So an example would be tightening or loosening of a nut using a wrench. So if you look at this diagram, we have our wrench. This is where your bolt or your nut is, and we are trying to turn the wrench to either tighten or loosen the nut. And you're applying a force at the end of this wrench. Now, how much torque is generated depends on two things: the distance between the bolt and the point where the force is being applied, so the distance from here to here, and the magnitude of the force that is actually being applied, so this force here. Now, the direction of that torque can either be into the material being bolted or away from the material of the bolt that is being loosened. And torque is measured in joules. So torque is just the magnitude of the cross product. The cross product between the torque arm, so its length, and the force. And based on the definition we just came up with, that's going to require us to multiply the magnitude of the torque arm, so the length of that wrench, the magnitude of the force, and sine of the contained angle. So let's try this out. A 60 Newton force is applied in a clockwise direction at the end of a wrench that is 20 centimeters in length. The force is applied at an angle of 80 degrees to the wrench. Calculate the magnitude of the torque and determine the direction the torque vector points in. Okay, so first of all, we are told that the wrench is being moved in a clockwise direction, which means that the bolt is being tightened. And if it's being tightened, then the torque is acting on the bolt into the material. So we already know about the direction here, into the material that is being bolted. Now, in terms of the diagram, we have our torque arm here, okay, coming from the bolt outwards. We're told that the torque arm has a magnitude of 20 centimeters, but we do need that measurement to be in meters because joules is Newton meters, not Newton centimeters. So I will make a note that it's actually 0.2 meters. We are also shown the force that is acting on the wrench, and the angle is 80 degrees. Now, if you notice the vectors, they are head to head, and we need our vectors to be tail to tail to use the appropriate angle. So I'm going to take this vector here and I'm going to shimmy it over so that it's at the tail or where the bolt is. I'm going to draw it as best as I can. It is going to have that same 60 Newton magnitude, and this force here should be parallel to this one, which means we can use a Z pattern to get that this angle is also 80 degrees. And now we're ready to go. Our torque will be the magnitude of the torque arm, so that's the 0.2 meters, the magnitude of the force that is being applied to the wrench, that's 60 newtons, times sine of the angle, which is 80 degrees. And if we put that into our calculator, we get approximately 11.8 joules. Therefore, the torque is 11.8 joules into the material being bolted. So that is one little application that involves the cross product. All right, so let's generalize this a little bit. If you have two non-zero, non-collinear vectors, then the cross product is defined as A cross B equals the magnitude of A, the magnitude of B times sine theta. So this right here represents the magnitude that we've been solving for. But to make it a vector, that magnitude is being multiplied by this vector n. Now, what is this vector n? Vector n is a unit vector that is perpendicular to the plane containing both vectors A and B. And the way we determine that direction is by using the right-hand rule. Now, I'm going to put vectors A and B just on a flat surface, and you're going to use your right hand to try to follow along. Now, let's say my vector A is here, and my vector B is here. If I want to do vector A cross vector B, I want you to take your right hand, open palm, and put it where vector A is. Now, if you can curl your arm in a natural way to get to vector B, then the direction that your thumb is pointing in gives you the direction of that normal. So if I do A cross B, from where my hand is at vector A, I can curl my fingers inwards to get to vector B, and my thumb is pointing up. So the normal here will be out of the page. And that will be the direction of the cross product of A cross B. But if you were to try the other way around, B cross A, if you again take your right hand, I have my thumb pointing up right now, and I place that open palmed hand at vector B, if I try to curl my arm to vector A, I would have to snap my fingers backwards to get to vector A. Not very natural. If, however, I take my hand and I flip it around, now my thumb is pointing downwards, and again, my palm is still open, and I line it up with vector B. If I curl my fingers inwards, I do curl towards vector A, and my thumb is going into the page. So if I take the cross product of B cross A, that normal vector that is perpendicular to A and B is going into the page. Now, some more notes about the cross product. We've already established the magnitude. The cross product is also known as a vector product or as an exterior product. Unlike the dot product, which was a scalar quantity, the cross product does give us a vector. And since there are two vectors that are mutually perpendicular to A and B, and since the cross product follows the right-hand rule, the cross product is not commutative, meaning if I do u cross v, it is not the same as v cross u. In fact, it's in the exact opposite direction. That's why the cross product of u cross v is the cross product of v cross u with a negative out in front, because they are opposites. And finally, before we get to a little example, if I take the cross product between the unit vectors I and j, so these are the vectors that follow along the x and y axis, well, what's perpendicular to the x and y axis? That would be the z axis, and that involves the unit vector k. What about j cross k? Well, these form the y and the z axis. The x-axis is perpendicular to that, so their cross product would be unit vector I. And finally, k and I, that's your z and x-axis, and your y-axis is perpendicular to both of those, which relates to unit vector j. Now let's try out an example here. Determine the cross product of u and v and u for the vectors depicted in the diagram. Okay, well, first thing, u cross v is going to be the magnitude of u, the magnitude of v, sine theta, times the normal. So the normal being that vector that is perpendicular to u and v. And in terms of that direction, we'll just say in or out of the page for right now. Okay, so magnitude is 30 and 20 and sine 40 for the angle. And if we punch that into our calculator, we get approximately 385.7 units. Now, in terms of the direction, take your right hand, palm open, my thumb is up. If I line it up with vector u, my fingers will nicely curl towards vector v. And in that setup, my thumb is pointing upwards, so it's 385.7 units out of the page. But if we do v cross u, we're still doing the same magnitudes being multiplied, sine 40, but this time our normal might be in a different direction. So we'll still have the same 385.7 units, but now if my thumb is up and I place my right hand palm open at vector v, I can't curl towards vector u. So I'm going to flip my arm around. My thumb is now going downwards. My palm is open. My right hand is on vector v, and now I can curl nicely to vector u, and my thumb is downwards. So our cross product is 385.7 units into the page. So these definitions that we looked at and these formulas are all about the geometric vectors, because we are using the magnitudes and the contained angle. But of course, we can also find the cross products of algebraic vectors. Now, here is the cross product. If your vectors are a and b, with a1, a2, a3 representing those x, y, z components, b1, b2, b3, the x, y, z components of vector b, this is your cross product. It is a vector, so I have one component, the y component, and the z component. Now that is probably very hard to memorize. So here is a way to remember the cross product. What you're going to do is take each of your vectors. So I'm going to start with vector A, and I'm going to write these coordinates in a row, but I'm going to start from the second one. So I'll write A2, A3, then I'll come back to A1, and I'll conclude with the A2 that I started with. Then I'll do the same thing for vector B. I'm going to start at B2, then B3, B1, B2. And then cross product, cross like an X, that's what I'm going to do. A2 times A3, B2 times A3. And look at that. That's what the X component is, but them being subtracted. So you're going to multiply your diagonals and subtract those values. Let's try again. A3 times B1, here it is, minus B3 times A1. Here it is, just written as A1, B3, but that doesn't matter. Then A1, B2, here it is, minus A2, B1. Perfect. So there's a nice little visual to help you set up your cross product and not have to memorize this formula. If you set it up nicely, your cross product is there right in front of you. So, some notes. The cross product of two vectors, a and b, is the vector that is perpendicular to these vectors. So when you do this cross product, that vector is going to be perpendicular to both a and b. With that in mind, that means the cross product can only be done in R3. You need that three-dimensional space. Because if you have two vectors in 2D, a vector that is perpendicular to both of them would have to be out of that page, which now makes it three-dimensional space. And the cross product represents another vector, so unlike the dot product, which is scalar. And finally, let's say you're not too sure if you set up your cross product correctly. You can always check your work. If you take the dot product between one of your vectors and what you think is the cross product, you should get 0. Because this should be perpendicular to both A and B. So the cross product with A, like with the dot product, is going to be 0, and B dot, the cross product, will also be 0. Just a nice little way for you to check your work. All right, so let's try our first algebraic vector cross product. We're given two vectors, A and B, and we want to find A cross B, and then we'll use the dot product to check our work. All right, so if I am doing A cross B, I'm going to set up vector A in a row, starting with the second term. So 3, 2, 1, back to 3. Then -6, 7, 4, back to -6. And now my cross product will be 21 minus -12. That's going to represent the x component. Then 8 minus 7. And then -6 minus 12. Clean that up. 21 minus -12 is 21 plus 12, which is 33. 8 minus 7 is 1, and -6 minus 12 is -18. Now, if you're not confident about it, let's try checking our work with the dot product. I'm just going to call this vector C. So, A dot, the cross product we just got, should give us 0. So let's take a look. For our dot product, we're multiplying the x components. 33 times 1 is 33. 1 times 3 is 3. -18 times 2 is -36. If we add those values, we get 0. So that means vector A is actually perpendicular to that cross product. Let's try vector B with that cross product. So now I'm doing 33 times 4. 33 times 4 is 132. Next, 1 times -6 is -6. And then -18 times 7 is -126. And if you calculate those, you get 0. And there's your check. All right. Let's just keep practicing that algebraic definition of the cross product while also connecting it to some properties. So I have vectors P, Q, R, and S, and we're going to calculate each cross product. So I'm going to set up P, starting with the second component, 3, 2, -1, back to 3. Then vector Q, -5, 6, 2, back to -5. And now we cross 18 minus -10. 2 times 2 is 4 minus -6. -1 times -5 is +5 minus 2 times 3 is 6. Clean that up and we get 28, 10, and -1 for that perpendicular vector. Now, We've already established that P cross Q and Q cross P shouldn't be the exact same vector. So let's see what is going to be different. So when I set up Q cross P, I'm going to put vector Q in my first row, starting with the second component. So -5, then 6, then 2, back to -5. And then vector P on the bottom, starting with the 3, 2, -1, back to 3. And now, -10 minus 18. -6 minus 4. 6 minus 5. Clean that up, and we get -28, -10, and +1. So our vectors are almost identical. It's just the signs are switched because they're going in opposite directions. So let's write that down. A cross B is going to be the same as -B cross A. Those two cross products are just opposite vectors. Okay, let's take the cross product of vector P with the resultant vector Q plus R. So I am going to calculate Q plus R first. So vector P is -1, 3, 2, and that's going to get crossed with, okay, let's add Q and R. 2 plus 3 is 5, -5 plus 4 is -1, and 6 plus -1 is 5. Now let's do our cross product. Okay, first vector starting from the middle term, 3, 2, -1, 3. Second vector starting from -1, 5, 5, -1. All right, so we have 15 minus -2. 10 minus -5. 1 minus 15. And clean that up. So that's going to be 17, 15, and -14. Let's try the next one. This one says, well, what if we take the cross product of P and Q, the cross product of P and R, as if I'm distributing that cross product in, and then I add my two vectors. Well, we already know the cross product between P and Q, so let's just figure out the cross product between P and R, and then we can add up those two vectors. All right, so to set it up, vector P, starting with the middle term, 3, 2, -1, 3. Vector R, starting with 4, -1, 3, 4. And we have -3 minus 8, 6 minus 1, -4 minus 9. And what do we get? -11, 5, and -13. Now we'll add this vector to the cross product of P and Q that we got in part A. So 28, 10, -1 plus -11, 5, and -13. And we get 17, 10 plus 5, 15, and -14. They're the exact same thing. So just like we could apply that distributive property to our dot product, we can do it for our cross product as well. So let's write that conclusion. A cross B plus C is the same as A cross B plus A cross C. All right, next, what if there's a scalar involved? 2 times the cross product of Q and R. Well, let's find that cross product of Q and R first, and then we can double it. So vector Q, -5, 6, 2, -5. Vector R, 4, -1, 3, 4. So that's going to be 5 minus 24. 18 minus negative 2. 8 minus negative 15. Let's clean that up. Double. 5 minus 24 is negative 19. 18 plus 2 is 20. And 8 plus 15 is 23. And now if I double that with that scalar, I'll have negative 38, 40, and 46. Let's see how that compares if instead of doing the cross product first, what if I multiply vector q by 2 first and then take the cross product with r? So doubled vector q will be 2 times 2 is 4, negative 5 times 2 is negative 10, 6 times 2 is 12, and we'll cross that with vector r, which is 3, 4, negative 1. All right, yet another cross product. Starting with the middle term, negative 10, 12, 4, back to negative 10. Middle term of vector r, 4, negative 1, 3, 4. Let's do the cross product. 10 minus 48. 36 minus negative 4. 16 minus negative 30. And what do we get? 10 minus 48 is negative 38, just like before. 36 plus 4 is 40, just like before. 16 plus 30, 46, just like before. So what this shows is it doesn't matter when you deal with that scalar of 2. You can find your cross product first and then multiply that scalar in, or you can do k times a vector and then take the cross product with vector b, or vector a cross k times vector b. It doesn't matter. Similar property that we have for the dot product. Finally, let's take the cross product between vector p and s. I'm just going to start off by writing those vectors since they're up at the top. Vector p is negative 1, 3, and 2. And vector s is 3, negative 9, and negative 6. Now, if you look at p and s, they look like they're collinear vectors. If I take vector p and multiply it by negative 3, I end up getting vector s. So these vectors are collinear. So what do we get for that cross product? Let's see. So 3, 2, negative 1, 3, negative 9, negative 6, 3, negative 9. All right. Negative 18 minus negative 18. 6 minus 6. 9 minus 9. Well, that just gives us 0, 0, 0. That's the 0 vector. So a cross b is equal to the 0 vector if and only if vector a and b are collinear. And that's it for the cross product. So practice quite a few of the algebraic cross product definitions while connecting it to these lovely properties over here. But of course, we also have that geometric definition that involves the magnitudes and sine of the contained angle.